Hi everyone, in this video I'm going to describe how we can extend all the geometric objects described so far, lines, planes, points, vectors, into higher dimensions. We went from 2D to 3D. Now we're going to go from 3D to 4D, and then 5 dimensions, and 7 dimensions, and 100 dimensions. And fortunately, almost nothing changes. Like all the math that we've learned already for things like dot products and length, it all stays the same. Now, why would we do this? Why talk about 10 dimensions when all that we really have is the 3 dimensions that we know? Going forwards and backwards, going left and right, going up and down, like those are our 3 directions. What does the fourth one look like? How about 10? What about 10,000 dimensions? Like, you can find discussions of these things, and some of them are philosophical in nature, and some of them look like they're talking about real dimensions. Now, we're not going to get too philosophical in this course. What we'll do instead of thinking about spatial dimensions is we'll generalize it to dimensions that have no spatial meaning at all. So, for example, you can have a vector that instead of defining distances that moving in the x, y, and z directions, you could have the components of the vector corresponding to prices of different objects. Let's say the x component is the price of an apple, the y component is the price of a banana, and the z component is the price of a pear. You can have that being your vector. Well, add a fourth dimension, add a fourth object, and just put a fourth price there, put a fourth number. You don't need to describe it in the same geometric terms, but all the mathematical machinery that we developed, vector addition, vector subtraction, and so on, it can all be used in this higher dimension. So here is a more concrete example. There's Kevin that has an investment portfolio, 2 stocks from company A, 4 stocks from company B, 7 stocks from company C, and 3 stocks from company D. And then Mary has a similar portfolio. We can express these stock holdings in vector format. So I would say maybe for Kevin, I'll use U for the vector. And for Mary, I'll use V for the vector. So U is equal to, the first component of this vector I'll say is the amount of stock or number of stocks from company A, 2, and then company B, 4, company C, 7, and company D, 3. And then for Mary, we have 4, 2, 2, 5 for Mary. The question underneath says, what does the quantity U plus V represent? Well, let's find U plus V. It's going to be 2 plus 4, 6, 4 plus 2, 6, 7 plus 2, 9, 3 plus 5, 8. What does it represent? Is the total of these stock holdings of Kevin and Mary combined. So if they were to combine their stock holdings, the vector addition is what would tell you what the totals of each type are. We would have to keep track of which component corresponds to which stock. We wouldn't want to change our minds halfway through the calculation and say the third component is now going to be some other company's stock for Mary than it is for Kevin. We want to be consistent so that we can do this type of vector addition and do and keep track appropriately. This is kind of a silly example because all we're doing is vector addition, but there's similar examples like this that can be done with more extensive things, including dot products. If you have a vector of prices and a vector of quantities, the dot product holds a particular meaning for that combination of vectors. So good news, there's very little new. This is almost review of the earlier part of the discussions of dot products and scalar multiplication and all those things. For example, the 0 vector in 5 dimensions is just 0 in all 5 components. The 0 vector in 4 dimensions is just 0 in all 4 components. The 0 vector in 12 dimensions is just 0 in all 12 components. So however many components you have, however many dimensions you have, the 0 vector in that many dimensions is just a whole bunch of zeros. That many zeros. The other no change property from previously is the idea of vector equality. If 2 vectors are equal in 4 dimensions, it just means the first component of one vector is equal to the first of the second. Then the second component is equal to the second component. Third is equal to the third. Fourth is equal to the fourth. So in this example here, we're told that u is equal to v. We're asked to find the values of a, b, c, and d. So a must be 4, since the first component is equal to the first component. B must be 4, since first is first. Since second is second. C must be 2. And D must be 3, just by the property of vector equality. For distance, recall how we defined the distance between 2 vectors in 2D and then extended it to a distance for 2 vectors in 3D. Well, that extension can continue forever. If you want the distance between 2 vectors in an arbitrary number of dimensions, it's just the difference between the x components of the vectors squared plus the difference between the y components squared plus the difference between the z components squared plus, and then just keep going, the difference between the next component squared, and on and on and on until you run out of components. Length is the same. It's the length of any vector in 2D is going to be the length of the x, is going to be the x part squared plus the y part squared, all inside a big square root. For 3 components, it's the square root of x squared plus y squared plus z squared. For 4 components, it's the square root of the first component squared, second component squared, third component squared, fourth component squared. So each of those added together. Not any change at all. Unit vectors are defined the same way. A unit vector in 2D and 3D is defined as a vector that creates a length of 1 using the above formula, the square root formula. A unit vector in 4 dimensions has the same definition. For example, this example is not finding a unit vector, this example is finding a length. We're given a vector in 5 dimensions, we're asked to find its length. So the length of u is going to be the square root of the sum of the square of the components. 1 squared plus 2 squared plus 0 squared plus 1 squared plus minus 1 squared. So 1 plus 4 plus 0 plus 1 plus 1. So 5, 6, 7, square root of 7 would be the answer. Okay, we're given a vector u and a vector v. We're asked to find the distance between them and to find the magnitude of each one. So this is a 3-part question. So let's find the distance between them. The distance between u and v, that's our notation for distance between 2 vectors, is the square root of, we have the x component minus the x component, so 0 minus 1 squared plus negative 1 minus 2 squared plus 12 minus 3 squared plus 7 minus 4 squared. So we have 1 squared, which is 1. And then the next one we have negative 3 squared, which is 9. The next one we have 9 squared, which is 81. And the last one we have 3 squared, which is 9. So that is the square root of 100, which is 10. That's one part. Now the next part. It's making beeping noises. I don't like beeping noises. Okay, next thing, magnitude of each. So that was length, or distance rather, that was distance. Now magnitude, or length, or norm. So the length of the vector u, that'll be the square root of 1 squared plus 2 squared plus 3 squared plus 4 squared. So that's the square root of 1 plus 4 plus 9 plus 16, which is the square root of 30, I think. Let me double check that. 4 plus 16, 20. 1 plus 9, 10. 10 plus 20, 30. Okay. Then the next length of v, as long as I plugged all the numbers in correctly. Okay, now length of v, we have 0 squared plus negative 1 squared plus 12 squared plus 7 squared. So 0 plus 1 plus 144, 12 times 12, plus 49. So square root of 194. 1 plus 49 is 50, and then 50 plus 144 is 194. Okay, next question. Should add a little arrow there above that vector. Create a unit vector in the opposite direction to u, 1, 3, 4, 3. So recall the steps that we went through the last time we talked about creating unit vectors. Step 1 is to find the length of the vector. Find the length of u. Step 2, create a new vector. Give it a name if you want, but you don't have to. U divided by the length of u. And then step 3, since opposite direction, put a minus sign in front. So minus u over the length of u. That's the 3 steps we're going to have to go through in order to find a unit vector in the opposite direction to this target vector. So we'll do the first step, find the length. Length of u is equal to the square root of 1 squared plus 3 squared plus 4 squared plus 3 squared. So the square root of 1 plus 9 plus 16 plus 9. So 35, I think. Let me double check, because this is where I make all my mistakes. So 9 plus 16, 25, and then 1 plus 9, 10, 25 plus 10, 35. Okay, just adding in different order is a good way to check your addition if you're doing it mentally. Now I'm going to create that vector. I'm going to do steps 2 and 3 at the same time. So this is negative 1, 3, 4, 3, all divided by the square root of 35, which means we divide each of those components by the square root of 35 and put a negative in front of each one. So we get minus 1 over the square root of 35, comma, minus 3 over the square root of 35, comma, minus 4 over the square root of 35, comma, minus 3 over the square root of 35. That's your answer. So it is a unit vector. It has a length of 1, and it is in the opposite direction of the original vector. The next thing we talked about with vectors was multiplication by scalars and multiplication of a vector by a vector. Scalar multiplication is exactly the same as it is in 2D and 3D, and so is vector multiplication with dot product. So we saw in the previous example already did scalar multiplication and multiplied this vector 1, 3, 4, 3 in a sense and multiplied it by negative 1 over 35. And it's true in general that c times any vector, where c is a constant, is just going to be each of the components of the vector multiplied by c. The definition of parallel vectors has no change in higher dimensions. Two vectors are parallel to each other if we can write one as a scalar multiple of the other one. For a vector addition and vector subtraction, we already did an example like this, but we'll do another one. There's no change, we just add or subtract the components. So in the first example, we have a 4-component vector and another 4-component vector. We're asked to add them and we're asked to subtract them. So the first, adding them, u plus v is equal to 1 plus 0, comma, 2 plus negative 1, comma, 3 plus 3, comma, 4 plus negative 2, which is 1, comma, 1, comma, 6, comma, 2. We do u minus v, it's component minus component, so 1 minus 0, comma, 2 minus minus 1, comma, 3 minus 3, comma, 4 minus minus 2. Now we simplify 1, 2 minus negative 1 is 2 plus 1, so 3. 3 minus 3 is 0, and then 4 minus negative 2 is 4 plus 2, so 6. For the next example, it's a combination of scalar multiplication and vector subtraction. So this new vector w is going to be 3 times the vector u minus 2 times the vector v. So I'll do 3 times the vector u, 3, 0, 3, 0, negative 3, 0. And then we're subtracting 2 times the vector u, 0, 2, 2, 0, negative 2, negative 2. So 3 minus 0 is 3, 0 minus 2 is negative 2, 3 minus 2 is 1, 0 minus 0 is 0, negative 3 subtract negative 2 is negative 3 plus 2, so negative 1. And then we have 0 subtract negative 2, which is 0 plus 2, so 2. And it's just more pieces to do, but the same thing that you always did for each piece. Another piece of good news is that the dot product didn't change either. If you take the dot product of two vectors, what you do is you multiply the first times the first, plus second times second, plus third times third. The dot product in higher dimensions still creates a scalar, not a vector. So for an example, in 4D, we're given these two vectors u and v and asked for the dot product. So u dot v equals 4 times 3 plus negative 3 times, I'll put these in brackets so it's not, doesn't look like a dot product, 4 times 3 plus negative 3 times 4 plus 5 times 5 plus 1 times 0. So 12 minus 12 plus 25 plus 0. We get 25 as the answer for the dot product. Angles. This is where we have to resist the urge to think too hard geometrically. What does it mean to have an angle in 7 dimensions? An angle in 2 dimensions is this. Well, there's another one, there's another one, another one. Angle in 3 dimensions is also this. Just rotate it around. And that looks ridiculous. It looks, now as ridiculous as that looked, I can't even do that for 7 dimensions. I can't even do that for 4 dimensions. Forget 7 dimensions. But we can define, despite not being able to draw it or picture it or make hand motions that describe it, we can still define the angle in 7 dimensions using the same formula that we used for 2D and 3D. That first, the dot product between two vectors u and v can be written as the length of u times the length of v times the cosine of the angle between them. And then we could rearrange that to isolate for the cosine of theta. Cosine of theta is equal to u dot v divided by the length of u times the length of v. This is insensitive to the dimension that we're in. Okay, so here we're asked for the cosine of theta given information about u and information about v. Okay, so cos theta is equal to u dot v we'll have 3 times 2, which is 6, plus 2 times negative 2, negative 4, plus 2 times negative 1, negative 2, plus 2 times 1, 2, and then all divided by the length. The length of u is 3 squared, 9, plus 2 squared, 4, plus 2 squared, 4, plus 2 squared, 4. And the length of v is 2 squared, 4, plus negative 2 squared, 4, plus negative 1 squared, 1, plus 1 squared, 1. Now simplify. 6 minus 4 minus 2 plus 2 is 2. And then simplify the square roots. 9 plus 4 plus 4 plus 4, so 9 plus 12, 21. And then 4 plus 4, 8, 9, 10. And that would be the angle. Don't simplify it, don't do anything weird. It is not necessary. Just like it wasn't necessary in 2D or 3D. The definition of orthogonality that we had before was that two vectors are orthogonal. Two vectors are orthogonal if the angle between them is 90 degrees. So you go back and look at this. Well, you have to know, to make sense of what I'm about to say, you have to know that the cos of 90 degrees is 0. That means that u dot v divided by the length of u times the length of v is 0. Well, the lengths can't be 0. That means if the angle is 90 degrees, then u dot v is 0. And we've been using that all along to test whether two vectors are orthogonal to each other. I just wanted to connect it back to the definition of the cos of the angle between vectors, because I don't think I did that in one of the prior videos. Forgot to mention that. So two vectors are orthogonal if u dot v is equal to 0, if the dot products between the vectors is 0. So we're asked to find the value of k that makes this happen. Find the value of k that forces the dot product between the vectors to be 0. So when we dot the vectors, we're going to get 2 plus negative 2 times 1 plus negative 4 times negative 1, so plus 4, plus 3k plus 2 equals 0. So after dotting them, now we can simplify. We get 6 plus 3k is equal to 0. Subtract 6 from both sides, so 3k is equal to negative 6, and then k is equal to negative 6 over 3, which is negative 2. That is the k value that will result in these two vectors being orthogonal, or being at 90 degrees to each other. Okay, some really good news is that there is no cross product in higher dimensions. The cross product only exists in R3. It does not exist in R2, does not exist in R4, R5, and R6. So we won't construct anything that is analogous to a cross product either. It's just not here. Just in R3. Okay, and we'll continue with the rest of the properties in another video.